welcome to the part 2 video of 7.3.4. This time we are going to be looking at Fenman diagrams as promised, and let's begin. So first off, a quick little reminder, with Fenman diagrams, it sort of puts together all of the information that we have learned together so far. So with Fenman diagrams, we have to keep in mind of conservation of charge, baryon number, lepton number, as well as strangeness. Now, interesting thing about strangeness is that it's not always conserved, and we will look at an example of that. Next up, some conventions for drawing Fenman diagrams. In terms of time, time always flows from left to right, the way you read. And so if something happens, if you see something happen on the left side, that happened first, then it became something else on the right-hand side. Next up, we have our arrow indicators of particles and antiparticles. So particle is indicated with an arrow pointing to the right, and an antiparticle is indicated regular. An antiparticle is indicated with an arrow pointing to the left. It doesn't mean it's going back in time. It just indicates that it is an antiparticle. Okay, next up we have, now both the textbook and, the textbook is a little bit more clear about this. The textbook likes to use the bosons, plus and minus, as well as a Z boson. They like to indicate this using the dotted line, but they don't always keep constant with this. Cognitive sort of interchanges the both, but Cognitive kind of uses the wiggly line the most. Now the wiggly line is an indicator for all the interactions that happens during maybe like a decay process or any type of interactions. Okay. Next up, we have vertexes. So each vertex, which has a circular dot on it, so little green dots that you're seeing there, every dot needs to have an arrow going in and coming out of it. Okay, so again, what we're actually seeing with something like this particular section right here is it's indicating that a particle and an antiparticle, so the up quark and the anti-up quark, are possibly annihilating or destroying each other, and then new things are being formed. So it could be energy for a moment. It could be the transitional particles, like the boson particles. Or it could be a photon that's going to reform itself as new particles. So that's what's going on there. Here in this particular example, we might have a typical transition. So it could be maybe like an electron picking up additional energy from a photon. This is just another example of that. So always remember that every vertex has to have an arrow going in and an arrow going out. Okay, next up we're going to look at question, our fifth thing here is that the wiggly lines can only have one wiggly line per interaction. Okay, so if you ever see two wiggly lines, that is incorrect. Okay, so down here, that is not the right way to draw a Fenman diagram. Okay, in terms of charge, charge has to be conserved before and after a vertex. So if there was nothing before, there has to be nothing after. But that's not very realistic. But this would be an actual example. So if there was a charge before, there needs to be a charge after, or if there was a baryon number before, there also needs to be a baryon number afterwards. Okay, moving on, we have some examples here. So this is the absorption of a photon in example number 1. The second one is a photon creating both the particle, the electron, as well as the antiparticle, the positron. Now note that the positron points backwards, it points to the left. Okay, so that's in line with our conventions. Next up, we have a neutron turning into a proton by giving off a negative charge. So remember that a neutron has a down quark instead of an up quark. So what the down quark does is that it's giving away a negative charge, and that's how it becomes positive. So by giving away a full -1, which is what the W negative boson there represents. So if you think about the difference, we go from -1/3 to +1/2. That's a difference of 1. Okay, and that's exactly what's going on there. Okay, it gives us the full 1. It flips into a 2/3 charge positive up quark. And also that with the extra charge that it's giving off, it's forming an electron and an anti-electron neutrino, which has a neutral charge. Okay, so that's how it conserves that charge there. Okay, example number 4, we have a cation, I think, and it has an up quark and an anti-strange. So this is a rather complex situation. So nothing really happens with the up quark. It goes into the pi positive. Now, if you think about charge here, we have a +1 here. We have a +1, +1, and -1. So that's essentially 0, and that's how the charge there maintains itself. With the gluon, so again, this is a rather complicated example here that it sort of comes from the observation of particle physics. And so the gluon creates usually a particle and the antiparticle. So the up quark and the anti-up quark, sorry, the down quark and the anti-down quark in this particular case. And the strange quark, this is kind of funny, is that the anti-strange quark is giving off a positive to become an anti-up. So strange is -1/3. The anti-strange, therefore, is +1/3. So remember, up is +2/3. Anti-up is therefore -2/3. So by giving away a plus, it becomes more negative as a result of that. Okay, and that plus then translates into the anti-up and into the anti-down and the up. Okay, so the positive becomes the anti-down and the up. Okay, and then from the up, there's some extra energy that comes out of that, and it's forming our down and anti-down. Okay, in terms of our work examples, let's begin here. So we have we have an electron, we have a positron, and what I did was I purposely drew that little arrow on top to represent that it's an antiparticle. We don't usually draw that part on top of it. And so what the diagram looks like is we have 2 lines pointing in. Now the one that points left to right has to be the regular particle. And the one that points backwards is our antiparticle, or positron. Okay. Usually we sort of put a little dot over that vertex. We do our squiggly line. And then this becomes our muon, which is our regular particle. So muon is normally a negative charge. And then so the antiparticle has exactly the opposite charge. So that's the muon positive, or positive muon. Okay, next up we have a pion. So you'll see this notation where they sort of like to hold the different particles together using a little bracket like that. It's got a positive charge. And we have the muon plus, which is the antiparticle. So muon plus is the antiparticle. And so these guys are, they're going to actually work together because we have a particle and an antiparticle. And they are going to convert themselves into our antiparticle. I'm going to move this over a little bit. So this is our antiparticle pointing in the opposite direction. And then we have our regular particle, which is a neutrino. Okay, let's look at our third example now. So in our third example, we have, now I kind of forget the the name of this particular symbol there. Sorry, guys. So if up, down, and S is the name of this particle, or what this hadron is made up of. And so it's forming a proton. So proton is up, up, and down. So that's our proton. Then we also have a pi negative. So the 0 there indicates that it is neutrally charged. And so we know that a proton is positively charged, right? We don't really write that. So with negative charge, so overall we get no charge, right? Okay, just gonna clean that up a little bit. So we don't usually write that, but we know it's positively charged. In this particular case, this is kind of, this is pretty fun. So what's going on there is, I'm gonna rearrange this a little bit. So I'm gonna write down and then an up, okay? So up, nothing really happens to it. Down, nothing really happens to that. Strange, and this is gonna sound strange. Strange is minus 1/3. Up is positive 2/3. Okay, so again, it's giving away a negative to become positive. So this time, a strange is actually turning itself into an up quark. Okay, so they're two regular particles, so arrow in, arrow out. It's giving away, as we said, a negative charge, so W negative. And then it spawns a particle and an antiparticle, which is down is a regular particle, and up is our antiparticle. Okay, so that's how we achieve that. Okay, last up, and again, this is, some of these interactions are pretty difficult to understand, and so they are quite challenging. You're not likely to get things of this higher level of difficulty without getting some hints. But you know, do be prepared in case they change things up on you, and try to kind of think things through a little bit yourself and how this might work. Okay. So last one, again, this is really, really complicated, but we're going to go through it just so you get a rough idea of what's going on here. So we have a particle, D neutral, and then it has a charm and an anti-up, and it's going to form two particles. It's going to give us a cation negative, and we're also going to get a pion positive. So pi up, anti down, strange, anti up. Now, we can already see in the notes here that this is, we already know the charm itself is going to change itself into a strange. So charm is going to convert itself into a strange. So strange was minus 1/3. Charm, I think, might be a positive. No, this is neutral. So anti-up has to be negative 2/3. That means charm has to exactly neutralize that. So charm must be positive 2/3 because that's neutral. So strange is minus 1/3. So it's giving away a positive, isn't it? Right? It's giving away a positive to become negative. So it's giving away a positive. Now, when it gives away a positive, again, it usually spawns a two particles, a particle and an antiparticle. So in this particular case, now again, when they write, when they present the information in this particular order, it actually gives us usually some hint about how it's supposed to turn out. Okay, so usually if you write it in that order, it's going to give you some ideas of, oh, okay, I've got a positive, and then, so we know it's going to create a particle and antiparticle, which is, we've got, sorry, I'm going to use pink. So we've got our anti and our regular particle. So, okay, let's go with that first, and then we'll have a little think about that a little bit later. So we have our antiparticle and a regular particle. So I'm just going to write that down. So up, remember, was plus 2/3. Anti-up is minus 2/3. Nope, that doesn't work out. That must be a gluon, okay? So a gluon is probably actually spawning that. So W plus wouldn't give a neutral. Our W negative actually has to give us a, sorry, red color. Okay, so W negative should actually give us our, no, W positive, sorry. Yeah, W positive is going to give us our positive charge. So, that I think then is actually going to give us our, it's going to give us this last little piece right here on the bottom. So let's have a quick little think about this. We have an antiparticle and an antiparticle, so arrow in, arrow out. Anti-down is plus 1/3, right? So that is actually working together. We've got a plus 1 here, right? So it's converting, this plus 1 is converting the up into, sorry, the anti-up into the anti-down. And what is happening here is actually a gluon that's forming this guy. Okay, now I suppose a different way. I suppose it could have actually worked out without the gluon, in the sense that I think a pi positive could actually have been spawned from this. So this is just one of the possibilities that could happen, but a pi the W positive could have definitely spawned the pi positive particle. So it might have also, I think this would also be an acceptable solution here as well. So up, anti-up will be anti-up here. Sorry, anti is going to be backwards. Charm to strange. This could form our, whoops. So this forms our regular particle and our antiparticle. And so yeah, that would give us our full plus 1/3. Actually, this would be actually a lot more simple, wouldn't it? Yeah, that would definitely be a lot more simple. Okay, so two possible solutions there. I think this is probably the more simple, maybe even the correct one. But with nuclear physics, multiple possibilities are there to create the possible solutions, as long as they obey all the laws or the conventions of the Fenman diagram, then you have done the right things. Okay, guys, that's it for today. We'll see you next time when we're going to look at some data from the LHC. And so it's more of an enrichment activity, but it will improve your understanding of nuclear physics, okay? So we'll call it an optional class, or an enrichment activity is probably the best word to call it. Okay, guys, see you next time. Bye-bye.